Hello and welcome to this third installment on the series of videos accompanying the book Random Number Generators, Principles and Practices. Now we're going to start looking at entropy sources. This was going to originally be a single video, but now it's going to be about 4 videos because it's a fairly deep topic and there are different types of entropy sources. So first let's look at some kind of definition of an entropy source. So what do? They take environmental noise. So that's physical noise, usually in electrical circuits, but it could be something like photon noise. So take a camera image and filter out the picture and just use the noise. It takes that noise and turns it into bits with some amount of defined min entropy. And it outputs a value, and the value is part of a set of possible values. Let's say you're outputting 8-bit values, there would be 256 possible values. 2 to the power 8 is 256. And so there's a set of values it could come from, and we just call that set of values x, and the individual value little x, which is an 8-bit value in this example. Often it's a single bit, sometimes it's 32 bits, it varies based on the circuit. So here's a diagram and a little bit of notation. So when you see the word big H sub infinity, we don't say H sub infinity, we say min entropy. So this is a definition defined by Alfred Renier. And so we're saying the min entropy of the value x in the set of values x is equal to 4. Now, we're just picking that number randomly. It has to be a number from 0 to 8. There's only 8 bits. The maximum entropy that could be there is 8 bits of min entropy. And so we've got this box. It's an entropy source. It's got an output, and it's outputting a value x. And if we say, well, what is the the maximum amount of entropy? Well, the number of states in x is 256. Log 2 of that, the number of bits needed to represent that many states, is log 2 of 256, which is 8. But we're only getting 4 bits of min entropy out, so we get 4 over 8 is 0.5, and that is the entropy rate. So we can think of that as being the number of bits of min entropy per bit of data. So here we've got 8 bits of data, 4 bits of min entropy. So it's got an entropy rate of 0.5, or sometimes we say 50% entropic, words like that, to say, oh, well, half of it's half random. If this was a bigger number, then it would be more random. So this terminology we might use: 50% entropy rate, min entropy of 50%, 50% entropic source. It is a 50% entropic source. Now, there are no inputs to this entropy source, and generally that's the idea, that the noise it is sensing is usually the noise in the built into the electronic circuits. It's the noise all around us as a result of quantum physics and their random interactions, which lead to the noise we see in electronics. So there are various types of sources. The first one we're going to look at in this video is the phase error accumulation sources. So the classic examples there are ring oscillators and fast oscillators with noisy sampling, and we'll look at both of those. Later on in later videos, we'll look at metastable collapse sources, sampling noises, amplifying noise, and racing noisy circuits. So starting out with ring oscillators. So what is a ring oscillator? A ring oscillator is typically a series of inverters. There has to be an odd number of them, 1, 2, 3, 4, 5, that's an odd number. And then you sample the output. So this is oscillating, and every now and then you sample some point in the chain and you'll get a 1 or a 0. And the hope is that that value is random. So let's look at why does it oscillate? Well, you've got If you've got a value on this wire of 1, then the inverter inverts it to a 0. And that 0 gets inverted to a 1, and so on. But since there is an odd number, you're going to find if you go 1, 0, 1, 1, 0, 1, 0, 1, 0, while this has a 1 on it, it also has a 0 on it. That's not going to work. And so at some point around this chain, you have a discontinuity. And that is represented on this node here, that this value is a 1, and it's received a 1 on the input, so it's going to turn into a 0. So now this 1 is going to become a 0, and then this 0 is going to become a 1, and then this 1 is going to become a 0, and so on. So this discontinuity point is traveling around the circuit. If you look at the output of if you look at a ring oscillator on an oscilloscope, you'll see, and you captured a single point in time for say a few microseconds, you might see an oscillating waveform like this. But if you triggered on the on one edge and you overlapped multiple samples, what you would find is there is some uncertainty in the length of each of these periods, these clock high, clock low periods. And so it would become a bit mushy because you're overlapping multiple samples. You'd see the falling edge be at multiple positions, the rising edge be at multiple positions, and then the next sample would be on a wider distribution because now you're adding 2 lots of random positions, and so on. It would keep getting wider and wider, and you can imagine further down the line, the uncertainty in where the edge will fall compared to this initial edge here is greater than the size of a single bit period or a single cycle period. And so if you were to sample here and you get some value, and then you were to sample, you would wait a period of time and then sample again until the uncertainty is large enough that you don't know what value you're going to get, you'll get a random value. And that's the basic principle on which these things operate, that you have a ring oscillator and it's got some average frequency of say 100 megahertz, and you're sampling it at a much slower rate, say 10 kilohertz, and then there are many cycles and the uncertainties should grow and you'll get random bits. Now let's do a little bit of math, and I've put the proviso here, it doesn't really work like this. At the end I'll point to some papers which describe in much greater depth the mathematics of ring oscillators. But this is, while it's not strictly correct, it gives the right sense of how this stuff behaves. So first, some basic statistics. We've got 2 random normal variates. So X is a distribution, it's a normal distribution or a Gaussian distribution with a mean and a standard deviation, Ux and sigma x. And we've got another distribution, Y, which is a normal distribution with mean Y and standard deviation Y. If we add 2 variates from these distributions together, we get another variate that fits another distribution, and we'll call that Z. And that has a normal distribution again of mean of X, mean of Y, plus the variance of X and the variance plus the variance of Y square rooted. So what you find is when you add normal variates, the resulting distribution or the standard deviation of the variance of the resulting distribution is just the addition of the two variances you've added. But if you want to get back to standard deviation, you then need to square root it. So after n rounds, the standard deviation is n times the standard deviation squared, because what we are adding is the same random or the same standard deviation. So we've got this standard deviation here. So this diagram is saying we've got a cycle, and then the start of the next cycle appears to be a little bit random, and the 2 bars here represent the standard deviation. And so the actual range is a bit larger than that, but one standard deviation is this size. And we'll call that sigma for obvious reasons. So we and we find with a little bit of math, which is here. So we're going to say the mean is 0, because what we're doing is each time we're looking at the cycle, we're assuming there is an average frequency that this thing is running at, and we're measuring relative to the expected fall time or rise time of the edge. So we're just going to say the mean is 0, because we're constantly updating where we are looking. And sigma is sigma. The standard deviation is sigma. So we say on cycle 1, the distribution is the normal distribution of a mean of 0 and the standard deviation of that distribution, sigma x. The next cycle, we've added the same sigma x. We've added it to itself. And so we get a normal distribution of a mean of 0 and the square root of sigma x squared plus sigma x squared, which is 2 sigma x squared. But if we leave it like this, and then we add another one, we're going to take the standard deviation that we've just got and add to it sigma. So what we find is we get, or add to it sigma squared and square root the whole thing. So we take this and we square it, because that's what we're asked to do here. We take the sigma that we of one of the inputs, and we which is this, and we square it. So we get sigma x squared plus sigma x squared, and then we add to it sigma x squared, which is this term. And then to get back to a standard deviation, we take the square root of the whole thing. And so we've gone from sigma x to the sum of 2 sigma x's square rooted to the sum of 3 sigma x's square rooted, and then it carries on in that fashion. And so you can say on the nth round the distribution is the normal distribution of a mean of 0 and the square root of n sigma squared rooted. So that's pretty simple math. And if you look at the resulting growth of the standard deviation, it looks like this. I just plotted it. And what I said here is the standard the original standard deviation was 0.001, so 1 in 1,000. And we find that it doesn't grow very quickly. So this 1 here is saying the standard deviation is the same size as the bit cell. And to get to 1, it's taking us 1 million cycles. And that's kind of logical, where you're taking the square root of 0.001 is 1 in a million, and it takes that, and you've got to add that many together to get the to a full bit cell's worth of standard deviation. But that's the kind of size you want. So you have to undersample these a lot, where you got a certain speed with a certain of oscillator. You need to sample it quite slowly, and this leads to one of the properties of ring oscillators, that they are slow. Now let's look at what you might do to improve that, both in terms of entropy and in terms of speed. So a common trick, and it was in the original paper that described ring oscillators and some of their properties, you take multiple of them and you XOR the results. And the idea here is, well, some of these ring oscillators might not be working, some of them might be locked. But as long as one of them is oscillating well and providing entropy, that the XOR function will just ensure that entropy remains at the output. That's not a safe assumption, and we'll go into why in a little bit. Then the other structure, the one I would advocate for, is you take your multiple ring oscillators, you just take each of those outputs. So you sample each of the outputs slowly, and here we've got 4 ring oscillators, so we'll sample a 4-bit word, and we'll feed that into an entropy extractor, which is in a future video what an entropy extractor is, but one that is tolerant of correlation and serial correlation. So correlation between these bits and correlation between sequential bits coming out of individual oscillators. And those kind of entropy extractors exist, so you can do that. The advantage here is obviously the output is faster. You've increased the source speed by a factor of 4, whereas here you started with a source speed of a factor of 4, and your what amounts to your extraction function, this tree of XORs, is then slowing it down back to the same speed as a single oscillator. So that's another problem with these XOR trees. Now, what's wrong with this? Let's say these oscillators tried to lock to each other at some either 1-to-1 ratio or some harmonic. You would find that the values that you're getting out here are highly correlated, and that means that the XOR function is now no longer going to be adding entropy very well. It's actually going to be cancelling. You imagine you had two equal oscillators. They were completely locked. They were giving the same value. So you're either getting 1, 1 or 0, 0 on this pair of wires. That would always get you a 0 out of the XOR. Like there might have been entropy in one oscillator, but when you add a second locked oscillator, you're getting no entropy out. It's subtracted, and it's not working well for you. So that's the problem with this. And the solutions that people try to apply is to create ring oscillators of different lengths so they can't lock, but that turns out to be a very difficult problem, and we'll take a look at a paper which addresses that in a little later. There's another thing going on here. Now I've just given a wall of text here because I couldn't think of a pretty diagram, but deterministic jitter versus entropic phase noise. What we're trying to get entropy from is the entropic phase noise. So there's electrical noise causing the cycles of the oscillator to be longer or shorter on each cycle, and that's random, and we're trying to accumulate that phase noise to get a single bit of randomness with high entropy. But that's not the only thing that's affecting the phase of the cycle. So we have the idea of phase noise, which is this random variation, but there's also deterministic jitter, which is external input to the circuit that is causing it to jitter back and forth in a deterministic way. Now, the most obvious input there would be a clock on a chip. So the strongest signal, the strongest interference you'll find on a chip with a circuit is the clock. And a digital chip is the clock, because it's usually running everywhere, and it's there are lots of buffers running clock, and the power supply goes up and down with the clock. When the clock fires, the power supply droops as all the logic is changing, and then it increases. So the power supply, well, it's not drooping a lot, it's just drooping a little bit, but it is going up and down with the clock, and that is one of the things which will affect the variation in the phase. So when you look at the output of a ring oscillator, you'll be seeing some random looking variation, but part of that is deterministic and part of it is actually random. And if you can predict what the phase jitter is as a function of interference, then you can subtract that, and then you have less what is clearly less entropy in the output. Now you might want to do that to calculate what your min entropy is, but if you're assuming you've got the entropy that you appear to have when it's really deterministic jitter, and the adversary comes along and says, aha, I know better than that, I'll subtract this deterministic pattern that I know you've got, then they might be able to say, we've got less entropy, and now we've got a smaller search space to look for your key, or something like that. So this is a problem you have in designing a ring oscillator entropy source, is knowing how much entropy you have, because you have to know how much deterministic jitter you have. One way of getting around this is to build coupled ring oscillators. So instead of trying to make two ring oscillators not oscillate at the same frequency and not be able to lock, just ensure that they do lock. So you make two oscillators and you route them very close to each other in two loops side by side, and then you sample the outputs and you get 2 bits out, and those 2 loops will lock together. They will operate at the same frequency, and they will both have output, but with the same deterministic jitter, but different entropic phase noise. So then you can subtract the 2 outputs from each other, and you cancel the deterministic jitter, but you increase the phase noise. And then you can look at that output and say, aha, this is how much, from the 2 outputs, you can calculate the deterministic jitter, but also then you can use that output knowing that you've eliminated it. So now we're going to look at a different class of ring oscillator. This is called the fast, well, I call it a fast-slow ring oscillator. This was used in the Intel i8-10 PCH chip and later chips. So this is the peripheral chip on Intel motherboards. We still have PCH chips on motherboards, and sometimes we don't if it's an SoC that has it all built in. But the original chip on which this random number generator was put was called the i8-10. So if you look at the Linux kernel driver, for instance, it will call it the i8-10 driver. But of course, there were many chips with this in. We don't use it anymore. Why not? Well, because as we'll see, it requires some analog behaviors, a voltage-controlled oscillator, for instance, and it became harder and harder to build those well as the feature size of the silicon got smaller and smaller. So around, I think 22 nanometer was the last silicon node in which this is the old 22 nanometer that Ivy Bridge about a little over a decade ago was using, and there's a new 22 nanometer which is used for low power electronics, but that's a different process. But so we this was built in those chips. What we found in 22 nanometers, it was quite difficult to make this thing work, and we could tell in later revisions it wasn't going to, or later processes, it wasn't going to work at all. And that was the generation where we also switched to the metastable type sources, which we'll look at in the next video. So we couldn't use this anymore because it became harder and harder to build. And what this does is it puts the noise in the sample time instead of in the loop. So in the previous ring oscillator, we had a loop with some noise and we are sampling it at a regular interval. Here, what we're saying is we take some source of noise, and what's used here is a resistor. And if you load it correctly, it will exhibit some noise, some Johnson noise and shot noise and various types of noise. And we amplify that noise because it's a very low signal noise. And we feed that into the control input of a voltage controlled oscillator. So we've got a voltage controlled oscillator. Its frequency is varying based on the input control, and we're pushing noise into that. So now we've got a loop which is very noisy. It has a lot of phase noise. And this is a relatively slow loop. And then there's also a high-speed oscillator. So this is just a high-speed oscillator. It's running at, let me remember, I think it was 100 megahertz. It might have been a gigahertz. It was quite fast. And then we have what's called a super latch. What that just means is it is sampling this oscillator, and because this is oscillating fast, you need a latch that's optimized so it doesn't always go metastable when you sample the output. It's fast enough to latch this high-speed signal. And the clock input is the output from this oscillator. So we're taking a high-speed oscillator, we're sampling it with a noisy slow oscillator, and we put it into they call it, in the diagram they call it here, which was taken from a paper by, it was an analysis paper on this entropy source by Cryptography Research. There is the digital corrector, which is really the entropy extractor, and then an output and a bus interface to talk to it. So the stuff we're interested in here is this stuff at the top. That's the entropy source. And so let's take a look at what is going on. So here's our fast oscillator, and it's going up and down quite fast. And then we're zoomed in on this, on the same time scale, this much slower oscillation. So you could think of this as being the edge and a little bit of the cycle, but the actual other cycle is a long way off to the left and a long way off to the right. We're zoomed right in on this edge, and it's got some variation. And again, I'm using the two sides of this, these two edge bars to indicate the standard deviation. And so I've roughly lined this up with a normal curve. And so it's saying that 34% of, or well, 68.2% of samples will land in this range, and then 13.6 around here, and 13.6 around here, and another 2%. So the actual variation is quite a lot larger. Whoops. And so now, when I'm sampling somewhere in this range, there are many possible ones and zeros I could hit upon. It's and so the effect here is we've amplified the phase noise. We're using the phase noise in a slow, noisy circuit to sample a circuit with low phase noise that's operating a lot faster. But in a single sample, it is as if we have multiple cycles of phase noise. So we've amplified the phase noise. We've made it larger relative to the frequency of the loop. So that's actually quite a good design of ring oscillator entropy source. It's just hard to build in silicon these days. And that was present in many generations of Intel silicon prior to 22 nanometer. In 22 nanometer, we actually had both the new and the old as a backup. And we ended up using the new metastable based one because it worked fine. Now we'll talk a little bit about problems with ring oscillators. This is from a classic paper that was presented in 2009 at the Chess conference by Marketos and Moore. And this is the diagram that everybody shows because it gives a very good idea of what's going on. Here is the output from the ring oscillator, plotted as a series of bits in an array. And then they injected some RF with an RF probe and caused the ring oscillator to lock to the probe. You can see it's 10 10 10 10, a little bit of a flip, and then 10 10 10. So it's going away from its natural frequency and being random to locking to the input frequency. It can't vary the frequency that much, so at some point it has to break out and skip a cycle, but then it starts again. So now we've got a quite non-random looking piece of data. What might you do if you were trying to guess the key value? If this first line contained the bits that were going into a key and you were asked to guess, what would you do? Well, I'd say I'd start by guessing 0 1 0 1 0 1 and so on, or 1 0 1 0 1 0. And then I would scan through, putting perturbations at fixed intervals until I found a match for that line of data. The amount of cases I would have to search for compared to simply guessing a full line of random bits is much lower. So we've lowered the entropy a lot. It's much easier to guess what a value is coming out. And then they tweaked the value a little bit, and then they got it to sync to a different pattern, and we see this now even lower entropy, where most of the time the output value is a 0 lined up with the sample period, and then the occasional 1. So a string of 0 is 1, a string of 0 is a 1, a string of 0 is a 1, and you can see how it would be the number of values you would have to search to find a line in this sequence would be to guess a line in that sequence would be much fewer, and so the entropy has been reduced greatly simply by injecting some noise into the circuit and perturbing it in a deterministic way that causes it to lock. So there's lots more to read about ring oscillators. I think I've given you a flavor of the two principal types of ring oscillator circuits. There'll be one in the metastable entropy source talk, which is a metastable ring oscillator, but I thought that fits in the metastable talk much better. So the paper which gave you this diagram is this one. It covers the effects of signal injection on entropy sources by Marketos and Moore. The frequency injection attack on ring oscillator based true random number generators. Everyone should read this. It's a good paper. There's a paper on the evaluation of the actual entropy in ring oscillators. So this is quite a good paper if you want to get into the math of the mathematics of ring oscillator noise. This is a good reference. And so when I said earlier on, it doesn't really work like this, what I meant was it works like this in this paper, and there's quite a bit more math where he separates out the different types of noise and what the distributions are and how it all adds together. We talked about the problems of deterministic jitter versus actual entropy. This paper, True Randomness and Pseudo-Randomness in Ring Oscillator Based True Random Number Generators by Beauchard, Bernard, Fisher and Valchetnov. Apologies for mispronouncing that. That's a very good paper which explains how to separate out those two variables and analyze it. And there's another paper here. This is in 2003. It's a lot earlier than the active research on ring oscillator characterization. This is 2009, 2011, 2010. Here, this is 2003. And this is not a paper about, this is a book, but it's a book about creating oscillators. It's got a chapter on making ring oscillators, and the focus of the chapter is how to make low noise ring oscillators, how to make stable ones. He's not trying to make oscillators for cryptographic purposes or to make random number generators. He's trying to explain how to make nice stable ring oscillators for other purposes. And so there's this chapter, Jitter and Phase Noise in Ring Oscillators. And it gives a lot of advice on what to do to make it have low noise. So a good thing to do is to read that chapter and do the opposite of what is suggested, and that will help you increase the noise. And that's by Ali Hajimiri, maybe. Don't know how to pronounce that either. So that's it. That's a quick run through of ring oscillators as entropy sources. The next talk will be using metastability to sample environments in noise in the environment and give you random bits with high min entropy. Thank you and goodbye.